Syracuse was a notable city for its rich Greek culture and as the birthplace of the preeminent mathematician and engineer Archimedes. The fort of Syracuse was the location of a Roman siege of the city, where Archimedes was believed to have invented several weapons that frustrated the Roman invasion. Our next video examines the feasibility of the Archimedes weapon inventions, like the solar death ray that supposedly set approaching Roman ships on fire and kept them away from the city walls. We shall also look at Archimedes' mechanical weapons like his catapults and the famous claw, which historian Dio recorded as picking up Roman ships and dropping them to sink into the sea. We shall also look at other mechanical weapons inspired by Archimedes, so please like and subscribe to receive notifications of our future videos. This video demonstrates the Archimedes buoyancy principle and its relationship to density, and our next video moves into another graphic demonstration of pressure in fluids with practical applications and examples. Now later we look at the Archimedes mechanical weapons and the feasibility of his famous solar death ray. Archimedes was born in Syracuse in 287 BC. He was the son of an astronomer and mathematician named Phidias. He was educated in Alexandria, Egypt, which was then the chief center of Greek learning. The Alexandria Library was of paramount importance to education and was founded by General Ptolemy's dynasty of Greek pharaohs after the death of Alexander the Great. It was preserved through the times of Julius Caesar and Cleopatra around 48 BC, which is also the subject of our upcoming video about Cleopatra VII. Archimedes was perhaps best known for his comical revelation Eureka moment of discovering buoyant force. The story goes that King Hiero of Syracuse suspected that his goldsmith had stolen some of the gold he was given to make a crown, so he asked Archimedes to investigate. The king, of course, expected that 1 kilogram of coin would make 1 kilogram of crown, but the goldsmith wanted to steal some gold coins and replace them with the cheaper silver coins, where gold is usually some 50 times more valuable than silver, so the goldsmith kept 4 coins for himself and replaced them with silver coins. But the goldsmith forgot about density. The density of a material is calculated as the ratio of its mass for a specific unit volume of the material, like so many grams per 1 cubic centimeter, and the density is also designated the Greek letter R, pronounced rho. And a dense material, like in this row 1 example, is tightly packed with matter, like atoms and molecules, and a less dense material, like the row 2 material, would be more loosely packed. So the density of pure gold is 19.3 grams per centimeter cubed, while the density of silver is around 10.5 grams per centimeter cubed. So gold is around 1.84 times the density of silver. So for example, the volume of 50 grams of silver is larger than the volume of 50 grams of gold. So since the goldsmith stole 4 gold coins, he had to replace them with 7 silver coins of the same size. So he added 3 more silver coins, thinking that no one would note the crown being a little larger, since it would weigh the same as the pure gold coins. Now Archimedes knew the simple fact that liquids take the shape of their container, and that the volume of the coins and the crown could be measured in liquid form, since you could melt them down if you wanted and then measure their volume. And gold is heavier than most metals, so any additional silver would increase the volume of an alloy crown. So you would get a larger crown with the same weight as the gold coin, but with less gold. But an easier way to measure the volume of the crown would be to use the water displacement method, where the volume of the water displaced by the original coins would be the same as the displaced water from the crown, and any extra volume would be equal to the volume of the 3 additional silver coins. But the displacement method is not very reliable for small volume differences, since the surface tension of water could hold small quantities of water from overflowing. So Archimedes came up with his buoyancy principle. Now, the buoyancy principle says that the uplift buoyant force on an immersed object is equal to the weight of the liquid that is displaced by that object, but of course in the opposite direction. Now, this infers that the larger the volume of the object, then the larger the volume of the displaced liquid, and so the larger the uplift buoyant force on the object. But in our case, both objects, the cheated alloy crown and the original gold coins, had the same weight in air, but in water, the alloy crown had a little larger volume, so it had the larger uplift force and was uplifted more to tip the scale. So Archimedes weighed the crown and the coins in air and in water. In air, the alloy crown weighed the same and kept the balance level, but in water, the alloy crown had larger volume than the coins, so it had more buoyant uplift force and tipped the scale. So for cheating the king's gold with silver, the goldsmith was put in irons. Now, buoyancy in fluids is a simple concept that we experience every day. We already know that objects weigh less in water than in air, and that swimmers feel lighter in water. On Earth, the mass of an object is pulled by gravity and turned into a force, which causes reaction forces. If you push on something, it's going to resist and either stop the motion or give way and move with it or through it. Now, whether the object sinks or floats depends on the object's overall density compared to the fluid density. Now, the heated air inside the hot air balloon expands, so it has lower density than surrounding air, which makes it lighter than air, so it floats. A submarine also remains neutrally buoyant at the same depth by matching its overall density to the density of the surrounding water, usually using ballast tanks filled with a combination of water and compressed air. So it's all about density and volume of both the object and the fluid. An immersed object would sink, float, or stay in static equilibrium depending on its overall density. But the concept of neutral buoyancy, or where an object has the same density as the surrounding fluid, is very interesting in understanding more about buoyant force, as we shall see later in this video. The buoyancy principle uses very simple math and free body diagrams. In air, as in all fluids, the weight of the object points downward, and the reaction or tension in the string of the scale points upward, assisted by the buoyant force, which is also pointing upward. At static equilibrium, the sum of all forces upward will be equal to the sum of all forces downward, and everything remains at rest, causing no movement. The buoyant uplift of air is too small compared to immersed objects usually, so it is mostly neglected in most static calculations, unless in the case of balloons, for example. But water is about 1,000 times the density of air, so the free body diagram remains the same, but without neglecting the buoyant force of water. So the object pulls down with this real weight in air, resisted by the two upward forces of the buoyant force and the tension or the reading on the scale, also called the apparent weight. So rearranging the equilibrium equation, the buoyant force is the difference between the real weight of the object in air and its apparent weight, as it's also shown on the scale. So what is the magnitude of the buoyant force? Archimedes says that the buoyant force on an immersed object is equal to the weight of its displaced liquid. So if we immerse a stone in water, the buoyant force would be equal in magnitude to the weight of the displaced water by the stone, but in the opposite direction. So why is that? To demonstrate Archimedes' principle for a heavier than water object, let's mark a boundary outline of a volume of water of equal size to a stone block. Since this water block is in static equilibrium, which means not moving, then the upward reaction R is equal to the weight of the water block. And in this case, R is also the buoyant force. Now, if we disturb the equilibrium by replacing that water block with the heavier stone block, then the additional weight of the stone block would overcome the uplift force and the block would sink until it meets a reaction force from the ground. Similarly, a lighter than water object, like a block of cork for example, would keep floating until it reaches equilibrium at the surface of water. The weight of water displaced by the submerged part of the cork is equal to the buoyant force on the object, but of course upside down. Now let's look at a simple exercise about free body diagrams. What is really the ground reaction of a sunken object that we mentioned earlier? Well, we already have two simple equations that we used, which is the weight of the stone block in air was equal to the buoyant force plus the reaction from the ground. And the second equation is that the buoyant force is equal to the weight in air minus the weight in water of the object. If we substitute one in the other, we get that ground reaction force supporting the sunken object, or Rg, is really the apparent weight of the object or the tension in the string of the weighing scale, which just rearranges the free body diagram. This is just another way of looking at the reaction force. So what's the magnitude of the buoyant force in air? Again, if we immerse an object in air, the buoyant force of the air on the object would be equal to the weight of the displaced fluid, in this case air. Archimedes says the weight of this displaced air is equal to the buoyant force uplifting the object. So if the density of the object is less than the density of air, which is 1 kilogram per cubic meter, then the object floats upward. But wait, air density is this big, 1 kilogram per cubic meter? That can't be right. Well, can this much air weigh 1 kilogram or 2.2 pounds? That's the weight of a pineapple or a toaster. Or, okay, over 2 cans of dog food. Well, air seems much lighter in this balloon. Well, what if you weigh this red balloon in vacuum? Then there will be no upward buoyancy lifting it, so you would get the true weight of the air inside the balloon. Similarly, recall that the water block in our previous example was at rest, suspended in water. So similarly, the air inside the balloon will be supported by the outside air, except of course for the weight of the empty balloon itself. So here's an interesting question. Can we say that all parts of a static fluid experience neutral buoyancy? Of course, we have to make assumptions to simplify our learning in stages. So if we go into more detail, we would note that the rubber material of the balloon itself compresses the air inside it. So the air density inside the balloon increases, which makes the balloon heavier than the outside air, making it sink to the ground. And again, in fluid statics, we usually assume conditions of standard temperature and pressure, and we usually ignore the compressibility and temperature effects on fluids. In our next video, we shall discuss density and pressure and use Archimedes' principle for practical applications and examples, like calculating the density of various materials and figuring out why do some swimming pools float out of the ground. Thank you for watching.